Hello guys, welcome back to EC TechNest. In this lecture, we'll be discussing about Module 3 of Embedded System Design, that is on RTOS and IDE for Embedded System Design. So what is an operating system? An operating system is a software consisting of programs and data that runs on the computer and manages the computer hardware, and also provides common services for efficient execution of various application software. So the OS layer interaction is in the form of user interacts with the application interacts with the operating system, and operating system interacts with the hardware. After that, hardware interacts with operating system, and operating system interacts with application, and application interacts with the user. So it is bidirectional process. Next is operating system basics. The primary function of operating system is to make the system convenient to use, and also to organize and manage the resources efficiently and correctly. So this is the OS layer and kernel services. So user application interacts with the kernel services. This interaction is mainly called the application programming interface, and when the hardware and the kernel services interact, it is called the device driver interface. Inside the kernel services, there are 5 different types of management, that is memory management, process management, time management, file system management, and IO system management. So types of operating system, there are 2 types of operating system classified, and they are GPOS, that is general purpose operating system, and RTOS, that is real time operating system. In GPOS, the operating system are deployed in the general computing system, and the kernel is more generalized and contains all the required services. Example would be Windows XP or MS-DOS for general purpose operating system, and it may inject random delays into the application software and thus cause slow responsiveness of an application. Coming to the real-time operating system, it is deployed in the embedded system, and it's demanding real-time response. Examples would be QNX, VxWorks, Micro C are examples of real-time operating system, and RTOS implements policies and rules concerning which are time critical and allocation of a system's resource. Next, we'll discuss about what a task is. Task is a piece of code or program that is separated from another task and can be executed independently. Uh, in an embedded system, the operating system has to deal with limited number of tasks. Multiple tasks are not executed at the same time. Instead, they are executed in a pseudo-parallel manner. That is, the tasks execute in turn as they use the processor. And next would be different bookmarks may be used to help read the identifier, read and identify where to resume reading next time. So in similar way, operating system also decides which task to execute in case of if there are multiple tasks to be executed. Next, we'll discuss about task states. Task states represent the states. There are 3 states of task, that is ready state, running state, and block state. Initially, it will be in the ready state. Depending upon the execution or on the task, it may be classified into 3 states. First one is running state. Only one task can be actually done using the processor at a given time. Therefore, it is in running state. No other task can be in the same state at the same time. After running state, it's ready state. In ready state, tasks are not currently using the processor but are ready to run when they are in the ready state, and then there may be a queue of tasks in the ready state. The third one is waiting state, in which tasks can neither be in running state nor ready state, but they are waiting for some external event to themselves to occur before they can go to the execution. So this is how you draw the FSM for task states transition, initially in running state and then ready state and then moving to blocking state. So this is how you write the transition diagram. Next is process. A process or a task is an instance of a program that is in execution, and difference between the process and program would be a program by itself is not a process, whereas a program in execution is known as process. So a program is a passive entity such as the contents of a file stored on disk, whereas process is an active entity and which is currently in progress. So process state is classified into 5 different types, that is new, ready, running, waiting and terminated. When it is in new state, that is the process is being created. When it is in ready state, the process is waiting to be assigned to a processor, and when it is in running state, instructions are being executed. When it is in waiting state, it is waiting for some event to occur, and when it is in terminated state, it is the final execution of the program. So this is how you draw the process state transition diagram. When it is in new state, the process is being created and then it moves to ready state. From ready state, it moves to running state, and after running state, it again goes back to waiting state. After waiting state, when the input output operations are completed, again it goes from ready to running and finally into terminated state. Sometimes when there is an interrupt that is occurred, the running state will again return back to the interrupt state. So next we'll discuss about process scheduling. Scheduling is a fundamental function of operating system in which we are scheduling the tasks and also giving priority based on the execution of the task. So the process control block contains many pieces of information associated with a specific process. First one is process state. The state may be new, ready, running, waiting or terminated state. And next one is program counter. It indicates the address of the next instruction to be executed. And CPU registers. The registers may vary in number and type depending upon the computer architecture, and it includes accumulators, index registers, stack pointers and general purpose register. So next one is CPU scheduling information, in which we include the priority pointers to schedule the queues and other scheduling parameters. The next one is memory management information, in which the information of the bar and the limit registers along with the page tables and segment tables are stored, which will be used by the operating system. And next one is accounting information. Accounting information would include the amount of CPU and real time that is used along with the time limits. And IO status information, it is used to track the input output devices allocated in a process. So this is how you represent a process control block. First you have the pointer and process state, process number, program counter, registers, memory limits and list of open files. Another very important concept would be threads. So application use concurrent processes to speed up their operation. Threads are mainly used to speed up the operation of the operating system. So to understand the notion of threads, let us analyze the switching overhead. So when there are multiple operations to be performed at a single time, we will be using the concept of threads. Consider the child process Pi and Pj of the primary process of the application. These processes inherit the context of their parent process. If none of the processes have allocated any resources of their own, their context is identical, that is, their state information differs only in the CPU states. Consequently, while switching between the Pi and Pj, many of the saving and loading of process state information is redundant. Therefore, threads exploit this feature to reduce the switching overhead. So, process and thread structure multi-thread. So, this is the structure. It has code memory, data memory, along with stack and registers with multiple threads. So, this is a technique which is called multi-threading. We also have a type of threads called POSIX threads, which is usually referred to as P threads, and its execution model that exists independently from a language as well as the parallel execution model. So the main thing here is each flow of work is referred to as thread, and creation and control over these flows is achieved by using calls to the POSIX thread API. That is, POSIX thread is an API defined by the standard of POSIX. There are many APIs that are available, that would be Solaris, Linux, Mac OS, based on the operating system. So The POSIX API and also within the third-party packages such as pthreads, which implements pthreads on top of existing Windows API. So this is how you declare the POSIX thread creation syntax. That is int pthread underscore create pthread underscore t star of new thread const pthread, and you are declaring the attribute here, and this is the handle that you are declaring. So, and this is the function of thread. Next we'll discuss about preemptive scheduling and shortest job first algorithm and round robin scheduling in the next lecture. Thank you.